I'm getting a lot of questions about the matrix transpose problem in the cache lab, and I thought I'd spend a little bit more time trying to unpack this for you a little bit. The first thing to note is that we are told in the lab assignment that architecture of the cache. We're told that there are little b equals 5 bits in the block offset portion of the address. So that gives us a block of 32 bytes, because 2 to the 5th is 32. We're also told that the value for little s, the number of set index bits, is also 5. So that tells us that we have 32 sets in our cache. We're also told that the value for big E, the number of lines per set, is 1, which makes this a direct map cache. So in order to figure out whether something is in the cache or not, we're going to use the set index bits, which are going to uniquely identify a set within the cache. And then we're going to check the valid bit in that location and compare the tag bits from the address with the tag bits in that one single line in that set. And if we get a miss, we're going to go fetch from the next layer down in the hierarchy. If we get a hit, then we can use the block offset to look inside of the block that's stored in that particular line to return the values. We know in this problem that we're looking at matrix transpose of a matrix of integers, which are always 4 bytes. So we can make some simplifying assumptions a little bit by saying that because we've got a 32-byte block, we can store 32 divided by 4, or 8 integers per block. Depending on what you're more comfortable with, you might think of a block as containing either 32 bytes or just think of it as containing 8 of those integers. I want to start with a simple example of this transpose problem and talk a little bit about the memory access patterns and how they affect the cache. So here, first of all, is matrix A. So this is the matrix that we're starting with, and we're trying to transpose it into matrix B. And I've indicated that as we move through matrix A, we're going to move along here row-wise, get the 0th row of A and put it in the 0th column of B, get the 1th row of A and put it in the 1th column of B. So A looks like this, B looks like this. We're filling in down the columns in B, whereas we're reading across the rows in A. Again, the unit here, the size of each of these little blocks here, is intended to be an integer, and I've indicated that up at the top here. I've got 8 integers, or 32 bytes worth of data in each row, and it just so happens that that fits in a single line of the cache, just to illustrate the principles here. In the naive algorithm, where we're just going to have, say, 2 nested loops that iterate over the rows of A and then go a column at a time and copy them into the columns of B, we'll see that basically the access pattern mirrors the way that the values in matrix A are stored in memory. We know that all C arrays are stored in row major order, so the values that are in memory are going to be first this integer, then this integer, then this integer, and so forth till this integer, and then the next one in memory is going to be this integer, and we'll just continue in that zigzag fashion across the whole array. The last location in memory is going to be that integer. So down here I'm trying to illustrate what's stored in memory and showing you kind of which of the rows are going to be stored in which parts of RAM. Again, I've tried to split this up into units of these 8 integers, or those 32 bytes, which just again happens to be a cache line size here as well. And I'm showing that address here in a sort of generic format where I'm just going to say, let's assume that we have a pointer to an array, let's call it A. The first value in this array A is going to be stored at the location pointed to by that pointer. It's just the way C arrays work again. So at A plus 0, we're going to have that first array element at 0, 0, then the one at 0, 1, the one at 0, 2, up through the one at 0, 7, which of course is this guy. And beginning with the next address in memory, we're going to have the first column of row number 1, which is going to be at array A, or at array A's base address plus 20 hex, which is 32 bytes. So we go from 0 to 32, and from 32 to 32 plus 32, 64, right? And all of the values in this range of memory are going to be those elements of the array that come from row number 1, this guy. And that's going to continue. Here's going to be the third row, row number 2, and on until we get to the last row of the array. And they're going to be stored in the same order as the rows of the matrix. Okay, let's take a look at array B then. Put this back up here for your reference, same diagram. Difference here is that the pattern with which we read from A is flipped over from the pattern with which we write to B. So the 0th row, which I've indicated kind of by this arrow, the way we're going to traverse matrix A, is going to be written into B in this order, down the column. However, matrix B is still going to be stored, like all C arrays, in row major order. So while in matrix A we had, say, this first row stored in a convenient fashion in memory to just access it directly, in matrix B we have the first value of this column and then the first value of the next column. And those guys are going to be consecutive, or those are going to be in consecutive locations in memory. Now let's go back here for a second and think about how the cache is going to behave. When we access this first element in A, just assume the naive sort of an approach to doing this. When we access that first value in A, we're going to look in the cache, and the cache is going to be empty to start with. So we're going to have a cache miss getting that value. We know that that guy lives here. We're going to get a cache miss with that access, but then because the cache was working with a 32-byte line size, we're going to fetch in the other 7 integers from that first row so that when we go to access this location in memory, it's already in the cache because we took the hit here. That's the wrong way to put it. We paid for the miss here, and that meant that the rest of the accesses to the values in that first row are already going to be in cache. So we get 1 miss followed by 7 hits on that row. It's different in B. We can see again, because everything is stored in row major order, that I've got a little different picture here. For B, I've got the first row in column 0, then the first row in column 1, then the first row in column 2, and so forth to the first row in column 7, moving our way across the matrix this way. Unfortunately, we're trying to write into the matrix going from top to bottom here. So if we think about the access pattern when we're writing into B, this is going to be the first location. That's in this spot, which is going to be read from memory. It's going to initially cause a cache miss, and then we're going to skip to this cell. Well, that guy lives here, which is in a different 32-byte block of memory, so it's going to also result in a cache miss. And then when we go to this guy, it's going to be another cache miss, and we're going to have to bring in this cache line. Now, if we had an arbitrary amount of space in our cache, this would not be a problem, right? If you think about the pattern back here in A, every time we move to a new row, we get a cache miss followed by 7 cache hits. In B, here we get a cache miss at the beginning of every row, but if those all stayed in the cache, when we went to the rest of the rows in succeeding columns, these values would all already be in the cache, and we'd get cache hits. So we'd see miss, 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 and so forth, miss. But then for the rest, we'd see hit, 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 and so forth through the rest of array B. That would be ideal, but we're going to see that we have conflicts between the reads from A and the writes to B. Let's unpack this a little bit more and look at what's happening with respect to the cache itself. So here I've reproduced array A and array B and showing the pattern here of moving across rows in A and down the columns in B. I've also filled in the address offsets here, so we'll assume that the array A is stored at location A plus 0, whatever A is, someplace in memory where the compiler allocated this guy. The first entry is going to be stored in the 4 bytes starting at A plus 0, and they're going to end up going through to A plus FF, which gives us the 64 values here in this, or 64 integers in this array. Now I'm also assuming, and this is the way that the cache lab works, that array A and array B are stored next to each other in memory. So right after array A is done, so ending at address A plus FF, is going to be the beginning of array B. So FF plus 1 is 100, which means that that first cell in B is going to be stored at address 100, and that's going to take us through to address 1FF. Remember that these arrows are the access pattern across the rows and down the columns, and not the way that the values are stored in memory necessarily. For array A, they are stored in row major order, but for array B, it's kind of working against the grain. We're accessing in columns, but the data are still stored in row major order. Now let's take a look at some locations in the arrays and where they're stored in memory. Excuse me, and where they're placed in the cache. So the first time we read a value from array A, we're going to go to A plus 0, 0, 0. So here's my schematic representation of that address. So I'm not paying any attention to the tag bits. They're going to be something, but we don't really care what. We're interested in kind of thinking about how the cache is affected by this. So I've taken that same picture of the address and how we're splitting out the individual pieces, and I've tried to carry the color through to these illustrations, where the lower 5 bits are this orangey color, and then the next 5 bits up from that are this green color, and then all the tag bits that I don't care about are up here just undifferentiated, and then I've got a couple of more bits here. I've grouped these physically then by bytes, right? So here's the least significant byte, the next most significant byte, the next most significant byte. So the color corresponds to the set versus block, and the grouping here corresponds to the actual bytes. So you can see at A plus 0, 0, 0, 0, I've got 0, 0, 0. Okay. So the location in the cache where this value is going to be found, if it's there at all, is going to be in the set whose number is just 0, right? 0, 0, 0, 0, 0 is our set index. And if we found it there, we would read it out at the location in the block beginning at position 0. Similarly, the value for A plus 1F, which would be the 8th integer in that first row, we unpack it in a similar fashion. 0, 1F is what we want to see here. So here's 0, 1F, which tells us that that is also in set 0, which makes sense, right? These all, because there are 8 integers in the row, and because there's space for 8 integers in the cache line, we would expect all the values in this first row to be in cache set 0. And if we scoot down to the end here, just to illustrate another location in the matrix, I've got A plus 0, 0, E0 would be the location where this first integer in the last row of the matrix is going to get stored. So 0E0 is here's 0, here's E, and here's 0. So we can see that 0E0 is going to be stored in cache line, which, well, I should say cache set, which is the same as the cache line. It's going to be in cache set 7. That's going to be where the first integer is located. And then the 8th one is going to be at location, it's going to end at location 0000FF. And 00FF is encoded with a 0 and then FF, right? So note that both of those values are in cache line 7 at different offsets, right? So this is the location of the final byte in A. Similarly, we can do this for matrix B as well. Again, because I'm assuming that A and B are right next to each other in memory, which is the case for the lab, we can say that because A ends at FF, we can assume that B starts at 0, 1, 0, 0, which is appropriately aligned to store integers. So the first integer in B is going to be at A plus 1, 0, 0. Here's 1, 0, 0. And we can see that because these 5 bits are the set index, that this is actually stored at set 8. Similarly, the last value in this first row at 1, 1F, which should be in the same set, is at, here's 1, 1F. And we can see that the blue bits here that are the set index are also set to 8. And then finally, at the end, we can see 1E0 to 1FF. Here's 1E0, there's 1E0, and 1FF, 1FF. And we can see here that these guys are stored at set 15, right? Here's the least significant bit of the set index is a 1, and then we've got 4 1s in the 5-bit set index, which is the value 15. And again, because these 8 values in array B are in consecutive memory locations because of the row major ordering, these extreme the ends of the row here are stored in the same cache set. So the question arises, well, are we going to end up with any kind of cache conflicts here if we transpose A into array B, even if we just use the naive go across rows in A and write across columns in B? Well, it seems pretty evident that because our last location in array A, actually the entire range of cache locations in array A are going to be between cache line 0 and cache line 7. And in array B, they're going to start at cache line 8 and go through cache line 15. And we know we have actually 32 cache lines. We're only using 16 of them, 0 through 7 for A and 8 through 15 for B. So we're not going to have any conflict problems at all with a matrix this size with this particular cache architecture. So a naive looping construct would work perfectly fine, would take maximal advantage of the cache. We'd end up with a miss and a bunch of hits for A, as we talked about before, and a bunch of misses and then a bunch of hits for B. Let's make the arrays larger. So here's a little bigger array. This is the shape of the very first of the matrix problems. It's a 32 by 32. Here you can see here I've labeled this. It's 32 integers wide. So all these little squares are integers or represent integers. And because those integers are 4 bytes wide, we've got 128 bytes along each of the rows. And then we've also got 32 rows. So going down this direction is also 32. You can see that because each cache line can store 32 bytes, we're going to have 4 cache lines per row of the matrix. So the first 8 values in array A here would be stored in one cache line. The next 8 would be in a potentially different cache line. The next 8 in a different cache line, and so forth. And I've illustrated that here with with the first few addresses here. So here's the very first line goes from A plus 0 to A plus 7F. So the very first line here then, if we decode this again, we're going to say 0, 0, 0, 0. Well, here's where that leading 0 is going to end up. Here's the second 0 is all zeros, third 0 all zeros, fourth 0 all zeros. So that basically tells us that the values in the first 8 positions of this first row in A are going to be stored in cache set 0. And they're going to be in locations from 0 to 1, 1, 1, 1, 1, right? But that's not the entire first line. We're going to also have another location for the second group of 8, for the third group of 8, for the fourth group of 8. And let's take a look at where this last byte of that first row shows up. It's going to be at A plus 7F. So here's 0, 7F. And you can see here that the cache set for this last chunk of that first row of A is going to be at cache offset 3, or cache set 3. And the very last part of it is going to be at offset all ones. And that makes sense, right? If this is the 0th entry in the cache and we're going across in row major order, this is going to be the 1th entry, the 2th entry, and the 3rd entry, the 3rd entry, which corresponds to these cache offset bits. Finally, let's take a look at where cache entry 8 begins, where the address at offset hex 80 begins. That's just the beginning of this second line. We can see here that it's going to be at A plus 080. Here's a 0, here's an 8, here's a 0. So as you wouldn't be surprised to learn, the place where that thing is going to show up is in the very next set of the cache, set 4 instead of set 3, where those 8 values would be loaded into the cache upon access. Okay, now let's look over here at matrix B. We've got a similar story here. I'm going to look at the first 2 rows of matrix B. So here at A plus 1000, which is where we end up with B located in memory, since it's appearing immediately following array A in memory. A ends at FFF, which means that B starts at A plus 1000. The location for A plus 1000 in the cache is going to be at 000. So the 1 here is the leading one in this offset that just sort of rolls into the tag. And then we've got 0, 0, 0. So this first row of B is going to be stored at set 0 at offset 0. And then here's 107F. That's going to be stored at set 3, offset 11111, as we'd expect, because it's 1, 2, 3. It's the 1, 2, 0, 1, 2, third line full of numbers in the array. It's going to be showing up in the third line. And then the very beginning of the next line is going to have a set offset of 100, and this is wrong. That bit should be a 0. It should just say 1000 and then zeros here. All fine and good so far, except for one problem. You notice that, let's just think about the very first row of A, and we'll just think about the first 8 integers in A. We want to read from those first 8 integers, and we want to write them into 8 integers here in B, going down the column. Well, if you notice here, the cache location for this first group of 8 integers in A is going to be in set index 0, but the first 8 integers here in matrix B are also going to be stored at set 0. So if we read something from A, we're going to see a cache miss because we haven't brought anything in from memory yet. We're going to bring in this first 8 values from A and then satisfy the read request from the first location. Then we're going to try to write that into B. Well, it turns out there's nothing from B in cache yet, but when we read in this first 8 bytes from B, we're going to go to the same set index, yet the tag is going to be different. I mean, whatever this upper portion of the address is, for sure we know that there's a 1 here and a 0 here, so those tags don't match. There's only one line per set in the cache, so the tags are not going to agree. We're going to evict from the cache the line that contains these values in A and replace them with these values from B. But now we're going to go back in A and we're going to access the next integer in that first row, which is no longer in the cache because it was evicted by B. So we're going to have a cache miss again, and we're going to have to reload the memory that contains this first 8 integers from A in order to read that value. And then we're going to write it back out to, well, where? Interestingly, because we're going down the columns here, we're going to have a cache miss on B as well, but that's kind of what we expected anyway, right? Because as we're working our way down these rows, we know from our previous discussion that each of these first references is going to result in a cache miss. So we're going to read in this guy at 1080, in other words, this entry, which is in set index 4. Now we're going to go back to the third element in A and read that in. Well, when we brought this guy in, we didn't evict this first 8 values from A, so they're still in the cache. So we get a cache hit here, and we write it into this location in B, which is again going to result in a cache miss and bring in the line containing these values. But again, that's what we expected would happen. And that's going to continue all across this first row of A. We're going to be loading in values as we access them, and it's going to result in a cache miss in the first group of 8 values from A. And then we're going to write into locations in B, which is going to result in cache misses. But only in the case here of A, we're only going to be evicting that value once because we're going to read in a conflicting location from B where we're at the diagonal, right? When we read in A, 0, 0, we brought in this line into set 0. Then we read this value from B, 0, 0, and we replaced that same cache line because both of them live in set 0. After that, we're going to get more misses across B here as we go, but the value in the first 8 integers from A are going to be read in again when we hit the second value in that first chunk, and remain in the cache for the remaining values from this first group of 8 as we populate the values going down B here. That's not going to cause a cache miss. So it's really that first the first guy that causes the problem here, where both the location in A and the location in B are in the same cache set, and therefore they cause each other to be evicted. Similarly, when we get to the second location in the second row of B, in other words, the second element on the diagonal of the matrix, right, the ones that are at index 0, 0, 1, 1, 2, 2, 3, 3, and so forth. When we get to the second row, we're going to load in the cache line that corresponds to these 8 addresses, and that's going to be at cache set 4. Well, that's going to be fine for this first value in that row, because that's going to end up being put up here in the 0th row of B. But when we get to the second one, well, that one is going to be this location, again, on the diagonal. And we know that because the values in this second row of B are stored in set 4, and we've already got set 4 loaded into the cache from reading across A, that we're going to get a cache miss at that location as well. And that's going to continue down through the matrix at every location where we have a diagonal read from A that's being written into B. We're going to have this collision between the cached entries from B and the cached entries from A that are going to make for one extra cache miss that we would really like to avoid. And that's really kind of the substance of the 32 by 32-bit portion of the lab. What you're trying to avoid is that cache miss. Okay, hopefully that's helpful. You probably don't need to draw as elaborate a diagram as I put together here, but it's certainly helpful to sort of write these things down, give yourself a little bit of a mental picture about what's happening in memory, and then think through the process of which locations in the arrays are going to be in which locations of the cache and when the conflicts can arise. So for example, in this 32 by 32 case, you'll see that if you can defer writing the value from the diagonal from A to B until after you've processed all the other elements in that block of 8 in this case, because that corresponds to the number of integers that we can stick in a single cache line. If you can defer it until after you've written all those other values, you can avoid having this cache collision between A and B.